All right, welcome back. We are continuing on with the 2012 intermediate paper, and we're almost done part A. This is the last little bit. We just need to do question 6 right here. Question 6. So let's take a little bit of a read, get the juices flowing, and we'll figure out how to attack this question. So integers can be written in bases other than the usual base 10. Okay. This is not new. Sometimes they invent concepts for these papers, but this is one that some people might be familiar with. Binary is a common base 2 that people are usually familiar with. But there's other ones like base 8, base 16, things like that. So, for example, the notation 235 with a little 7 stands for using base 7 representation. Stands for the base 7 representation of the integer. And this is how we calculate what it is. So it's 2 times 7 squared. So the first number gets the 7 squared plus 3. That's the second number. Times 7 plus 5. And he'd be times 7 to the 0. So we have 7 to the 0, 7 to the 1, 7 to the 2. Similar to how base 10 expressions, we have the 1s, we have the 10s digit, we have the hundreds digit. It's the same sort of thing, except in base 7 we don't have 100. So things like that. So if we were to perform this calculation, we'd actually get the number 124 in base 10. So what does that mean? 2 7 squareds plus 3 7 plus 5 is the same as 1 hundreds plus 2 10s plus 4 1s. Okay? That's just base 7 right there. So in general, if x and y are integers between 0 and 1 less than our base, right? If we're talking about base 10, we go from 0 up to 9. Those are the only digits we have. So if x, y, and z are integers between 0 and b minus 1 inclusive, then x, y, z little b can be calculated, so that's a base b number, that can be calculated as x times b squared plus y times b plus z. Okay. So that's the contest, giving us a little bit of a crash course in different bases. Okay. Question we're asked is find all triples x, y, and z. So I'll find all sets of numbers x, y, and z for which x, y, and z as the base 10 representation is twice x, y, and z as the base 7 representation. Okay? And since we're talking about a base 7 representation, we can't just have 8 and 9 as digits. These digits are going to have to come from 1, 2, 3, 4, 5, and 6. So even though 0 is possible, they're leaving off 0 as one of our possible digits. Okay. So this question might be a little confusing if you haven't seen bases before. So it's best to try and read it very carefully, go back and see exactly what they're talking about, and see if you can get a handle on it. Okay? You don't actually really need to know what bases are to do this question, but it certainly helps in terms of intuition. All we need, if you take a look at the question, all we need is this last little bit here. Okay? X, Y, Z in brackets with a little b is written like this. So all we're really doing is we've come up with this sort of function, and we're just equating these two functions, and we're limiting our entries to 1, 2, 3, 4, 5, and 6. That's really all this question comes down to. It can seem very overwhelming, but that's really all it is. So what we're going to do is we're just going to equate these two sort of expressions. All right. So we're on to question 6. So what do we want? We want x, y, z in base 10 to be 2 times x, y, z in base 7. Okay? So we don't actually need to know what these mean. We just need to know that the left-hand side is x times 10 squared plus y times 10 plus z, and that is 2 times x times 7 squared plus y times 7 plus z. Okay? we're just using this bottom expression here. That's all we need to use in order to do the question. Okay, that's all we'll need. The rest of it is just explaining to you how bases work and what they are in case you're interested or in case you're familiar. Okay. So what are we going to do? Well, we're going to likely expand these expressions. 10 squared we can write as 100. And then what we're going to do is we're probably going to bring all the x's onto one side, all the y's onto another. Okay, so that's 100x plus 10y plus z is 2 times 49x plus 7y. We're just rearranging it. We like to have our numbers in front of our variables or our unknowns plus z. Okay, so we can almost equate these two and start manipulating and bringing x's over, but we have this 2 over here, so we're going to have to multiply him through. So 49 times 2 is going to be 98x. We're going to get 14y, and then we're going to have 2z. And now we can start bringing the x's over to one side, the y's over to another, the z's onto one side, and we're going to get ourselves an expression. Okay? So I notice 100 greater than 98. I like keeping things positive, so what we're going to do is we're going to subtract 98x from both sides. We're going to be left with 2x on this side. Okay? 98x minus 98x, that's 0x, and then 100x minus 98x, that's 2x. I see over here I've got 14y, 10y. I'm actually going to subtract 10y from both sides so that I have a positive number of y's over here. So 14y minus 10y, that's going to give me 4y. And likewise, I see that I have 2z over here and just a z over here. I'm just going to cancel out that z, and we'll be left with this expression. So, having done that, all we now really need to do is answer this question. For x, y, and z amongst the numbers 1, 2, 3, 4, 5, and 6, which triples satisfy this equation? 2x equals 4y plus z. Okay? Now the first thing I notice right off the bat is that our expression 2x plus 4y equals 2x equals 4y plus z. Sorry about that. 2x equals 4y plus z. I notice that I've got a 2x, so that's going to be an even number, equals 4y, that's an even number, plus z. So I notice that if z is odd, this expression, no matter what I pick, is not going to make sense. So notice z is even. That's what we need. We need z to be even in order for this expression to work. Okay? We need the x, the y's, and the z's to come from 1, 2, 3, 4, 5, 6. And now we know that z is even. Okay? So what we could do is we could stop and try and see, okay, well, maybe there's some or some multiples of 4 stuff going on here, but really, now that z has to be even, we've just narrowed ourselves down to 3 different cases. Z can be 2, z can be 4, and z can be 6. So, if z is 2, what are we looking at? 2x equals 4y plus 2. We divide through by 2. Okay, we get x equals 2y plus 1. So now we just have choices for y. So the first thing y can be is 1. And if y is 1, can we get a valid x? Yes, we can. X would be 3. Okay. How about if y is 2? Well, then what would x have to be in order for our original equation, this one up here, what would x have to be in order for that to be satisfied? Okay. Oops, sorry. Getting ahead of myself. Two times 2. Oops. So that's going to be, I've changed the color. There we go. It's going to be 5. 5, still a perfectly valid number for what we're dealing with. Okay. How about if y is 3? Okay. Then what are we going to get? Well, we're going to get x has to be 7. And unfortunately, x can't be more than 6. X can be 1, it can be 2, it can be 3, it can be 4 or 5 or 6, but it can't be 7 or higher. So for anything else, actually, it turns out we get no other x values will work for us. So right now we just have these two. So if z is 2, y with 1, and x with 3, that'll work. If z is 2, y with 2, and x with 5, that'll also work. And we could stop right now and actually use some of our knowledge of base 10 or just plug these possible triples back into the original equations just to make sure that we haven't made an arithmetic error. But I'm not going to do that. I'll leave that up to you. Checking is very important, but let's continue on. So for our z equals 2 case, we're all set. We got 2 possibilities coming from that. And let's take a look at something else. Okay. So that was z equals 2. Remember, z can only be even numbers. How about z equals 4? So what does our expression become? This is the one that we need to solve. If we can get x, y, and z to satisfy this, then they'll satisfy the original equation. So that's x is 2y plus 2. So as before, we can just run down a list of, okay, what can y be, and then what values of x do we get? Two, 1 plus 2, that's going to be 4. Can x be 4? Absolutely. Okay. How about if y is 2? Well, then x would have to be 6. But that's okay. X can be 6. X is allowed to be 6. Okay? But once again, if we go any higher, once again I've changed color. Okay? So let's just imagine, what if we put in y equals 3? Well, then x would have to be 2 times 3 plus 2, which is 8. So that's not going to cut it. Once again, we have 2 cases that work. So x equals 4, y equals 1, z equals 4, that should be a triple that works. X equals 6, y equals 2, z equals 4, that should also work. Okay. So our last case here, the last possible even number that z can be is z equals 6. Okay. So what's our expression? Well, it reduces to x is 2y, as usual, but now plus 3. Okay. So we begin as usual. If y equals 1, then what would x have to be according to this equation? You'd have to be 5, and that's just fine. How about 2? Well, 2 usually works for us. X would have to be 7. And we're not allowed to have x as 7. So in fact, it turns out if x is greater than or equal to 2, no values of x work. Okay? And we've run out of cases. Okay? We got our cases z equals 2, z equals 4, z equals 6. So we have every single possible combination of the numbers 1, 2, 3, 4, 5, and 6 that satisfy this equation down here, and hence satisfy this equation up here, the one that we're trying to solve. So we can summarize our work a little bit. But let's just double check and make sure we know exactly what the question's asking for. Find all these triples. Okay? So we just need to list them out. We're not asked for the number of triples, we just need to find the triples. Okay? So I'm going to say the valid triples, the valid x, y, and z are, okay, we can start listing here. We'll go back to the other page to figure things out. So on this one, x equals 5, y equals 1, and z equals 6. That works. How about the case where z equals 4? X equals 4, y equals 1, and z equals 4. That worked. And x equals 6, y equals 2, and z equals 4. That worked. So now let's just take a look, see what the other ones were. X equals 3, y equals 1, z equals 2. X equals 5, y equals 2, and z equals 2. So 3, 1, 2, and 5, 2, 2. These are the other triples that work. So 3, 1, 2, and 5, 2, 2. So these are the only triples that work. There's 5 of them, and we've listed out exactly which ones they are. Again, if we wanted to, we could go back and we could check. I mean, even if our calculator has a base function that allows us to switch to base 7, we could easily check that sort of thing, or we could work it out by hand using the expression for different bases that we started with. Any of these will work. And it's always a good idea to double check your work. But even if we knew that all these ones worked, it wouldn't be enough to show that there is one that we're missing. Which is why, do one just to make sure you're on the right track, but doing all of them would be a bit of a waste. What you really want are just to get all of them. And so our case-by-case work here, by realizing that z needed to be even, we cut our workload in half. And then at this point, we didn't try anything fancy. We just said, okay, if z is this, what can x and y possibly be? Okay. And we got our 5 solutions, our 5 valid triples. So we write them down, and we're ready to move on to part B. Okay. So join me as we begin part B of the intermediate contest next time. Thank you.